Thank you so much. Thank y'all for joining us today. We're very excited to be giving this talk. My name is Richardson. I'm a researcher and software developer in the MGGG Redistricting Lab that's part of Tisch College of Civic Life at Tufts University. With me today is data scientist Dr. Karin Knudson, who works in the Data Intensive Studies Center that is also at Tufts University. And not with us today, but somebody that we do want to mention is Gabe Schoenbach, a former lab member in the Redistricting Lab, who made a lot of key contributions to the package that we'll be talking about today. So this package that we're talking about came out of research at the Redistricting Lab, which is primarily focused on civil rights data research. So under the direction of mathematician Moon Duchen, we have developed software for redistricting support. We've created an open source web app that allows anyone to draw a map for their state called Districtor. And we've researched redistricting related topics from computational, mathematical, and political standpoints. And many of us within the lab are really active in the process of redistricting litigation and supporting civil rights groups like the NAACP LDF and the Lawyers Committee for Voting Rights. Over the last several months, we've really been in the heart of the decennial redistricting cycle. So when the new census data comes out every 10 years, you have all this new information about the political and residential makeup of states, and the maps have to change. But since this process has started last summer, a lot of things have been up in the air on top of just the hectic process of analyzing new maps. Maybe I'll follow the news. I didn't want to mention the news. It's a little depressing around redistricting right now. But we're also dealing with some of that as well. And kind of aside from all of the legal stuff surrounding redistricting right now, it's just an involved process. When a state proposes a map, people and groups have a chance to disagree with it and take a case to court for any number of reasons that they may disagree with the map. But to that end, a lot of researchers have found various metrics that help quantify some of these legal provisions surrounding districting maps. And today, a thorough analysis of every map has to be conducted to ensure that the map complies with both federal and state level standards. The Voting Rights Act is one big set of guiding principles that map makers need to be thinking about as they're drawing. And so the VRA may be something familiar to a lot of you, but when it was signed into law in 1965, it protected voters of color from discriminatory practices that may have prevented their ability to register or cast their votes. And immediately after it was signed, there were really tremendous impacts. 250,000 new Black people voted or registered to vote for the first time by the end of 1965. And a lot of southern states, kind of as shown here, experienced great increases in Black voter registration. But the map does a lot more than just sort of protect against these registration practices. So one big clarification of the VRA came in 1986 through the Thornburg versus Gingles Supreme Court case. This case actually arose out of North Carolina when the state's map was sued for diluting the voting power of minority voters. And at the time, the Supreme Court actually unanimously decided that this was a VRA violation. And so from this, 3 new criteria, now known as the Gingles factors, came out of this that have to now, evidence of Gingles factors have to be shown in order to advance a VRA case. And so the VRA can only actually be used in redistricting litigation when racially polarized voting is present. And racially polarized voting implies kind of what the name says. There's clearly opposed preferences for candidates along racial lines. And in this context, we're specifically looking at whether groups in the state, or voters in the state's majority groups, oppose minority voters and block them from electing their candidate of choice. So Professor Duchen and a lot of the collaborators of the lab will often be called on to be expert witnesses for these redistricting litigation cases. Experts are called on to do so many different things. They may analyze a state's map or they may draw new ones altogether. But RPV cases always sort of center around the VRA and look at these Gingles criteria. So specifically, Gingles 2 involves showing that minority voters vote cohesively, and in Gingles 3, experts need to be able to show that the majority group is indeed block voting against the minority. This has become standard practice for witnesses to find these evidence of these Gingles factors. And while we see that this is a really important thing to be able to talk about in court, we're kind of faced with this big problem. The US uses secret ballots. So other than knowing how people voted in election totals, we really don't know anything about the voters themselves. Luckily, when local election officials tabulate these votes, they usually do it on the level of precincts. And precincts are just geographic areas of about 1,000 to 2,000 people who all vote at the same polling location. And then simultaneously, we have the census data that can also be put onto precincts. And using this in combination, there are statistical methods that can help us infer the voting powers, the voting preferences of different racial groups. And so, for example, if there's a precinct with a large share of Black voters and they prefer a certain candidate, and we sort of see that frequently, then we might infer that Black voters prefer that candidate.
So as Chanel explained then, this question of whether and to what degree voting is racially polarized is crucially important in some voting rights cases. I'm going to talk a little more about what this question looks like as a statistical problem before getting into our Python library for methods called PyEl. So essentially what we have access to in making estimates about racially polarized voting are the marginal counts built by cross-referencing census data with voting records. That is, in a table like this, we have counts of votes from election data and demographic info from the census data. We have one such table per precinct, and we'd like to, from these marginal counts, make inferences about the information encoded in the internal cells of the tables. We'd like to say something like X% of people in racial group 0 voted for candidate A, and so on for every combination of group and candidate. And I'm using the language of candidate here, but we might also be interested in voter turnout, in which case voting, not voting, or abstention would be another sort of quote candidate column. Ecological inference is the name that's been given to the general problem here, where we seek to make inference about the internal cells of such table using the aggregated behavior data in the marginal counts or fractions. So generally speaking, we have data that's been aggregated one way, and we want to see how it disaggregates into a different set of categories, here by voter race. And various methods for ecological inference have been proposed. I'm not going to go through them exhaustively, but I want to give a flavor for how this kind of inference might proceed. So one of the very simplest approach you could take would be something called ecological regression, which is a simple line-fitting approach where you model the vote share that a candidate receives as depending linearly on the proportion of voters or population within a group. So each dot in this plot is a precinct, and we're plotting the proportion of voters in group 2 on the x-axis versus the vote share for, say, candidate A on the y-axis. And if we extrapolate along this line, we see that this simple model predicts that if we had only group 2 voters, then the support for candidate A would be about 25% of the vote. So we could use that 25% from where we get to 1 on the x-axis as our estimate of the support within group 2 for candidate A. This linear approach has problems with it, but I present it here to give one simple way that we can make statistical assumptions that get us from data to estimate in this context. More recently and more commonly, within the last 25 years, a number of Bayesian hierarchical models have been proposed for ecological inference. And here's a relatively simple example of one approach for the case where we have only 2 groups and 2 candidates. This was proposed by King, Rosen, and Tanner in 1999. So in this setup, the B quantities highlighted here are the support from each group for each candidate A. And there's a lot going on here, but let's just focus on the last 2 lines. So we model the total votes for A within a precinct as a binomial distribution. So each voter votes by essentially flipping a coin with probability theta of voting for A. And where does theta come from? If we look at this second to last line here, we see that we're assuming that theta is this linear combination. So fraction of voters in group 1 times their support for A plus the fraction of voters in group 2, that is not in group 1, times their support for A. If we look further up the slide, we see this hierarchical element where the support levels B for each of the precincts, where precinct is here indexed with I, are drawn from some polity-wide parent distributions. This lets us share statistical strength across precincts while still allowing these voter preferences to vary somewhat from precinct to precinct. And these preferences are a key quantity of interest that we're going to learn from the data. EI models can get more complicated with variations like bringing in additional covariates, including more candidates and more racial groups, and or directly modeling the internal counts rather than just fraction of support. And all of these models make assumptions and ultimately rely on some ideas we have about groups behaving at least somewhat consistently across precinct. If you want to hear more about the specifics of the models, please find me in the hallway, and I will totally talk your ear off about the details. But for now, we'll move onward so we have time to get to the Python. I do need to mention, though, that a really nice thing about the kind of Bayesian models that we're working with here is that we can get samples from the distribution of these support values given the data. That is, we have not just one point estimate, but rather a whole probability distribution characterizing our degree of belief about the possible support levels within each group and for each candidate. And this is the posterior distribution. It describes the probability weight we assign to each possible support level after we've seen the data and under the assumptions of the model in our prior. We see in this plot, for example, that we have a lot more uncertainty about the preferences of groups 0 and 1 in green and orange than we do about the preferences of group 2, which is that narrow distribution in purple, centered closely around 25% or so. And the kind of algorithms that we'll use to obtain samples from the posterior distributions are called Markov Chain Monte Carlo, or MCMC methods. And MCMC methods are used to make Bayesian inference practicable in an enormous number of application areas. Broadly speaking, they give a stochastic way to step around the sample space, so to step around different possible values of our parameters, B, C, D, et cetera, recording the values reached at each step, such that when we look across a long enough chain, the distribution of the samples we obtain approximate this true posterior distribution that we're interested in. So the results from this family of methods, of which I presented two little examples, are the industry standard used to determine the degree of racially polarized voting. And we're therefore motivated to create an ecological inference library, PyEl, that brought together all the common EI methods in one reliable place and facilitated analysis. So we sought to support two main groups of users. First, practitioners using the results of ecological inference to inform voting rights cases, and second, researchers exploring new methods for EI. And members of our lab fall into both these groups. We're practitioners, but we also work on developing new methods. Existing implementations of EI were scattered across several R libraries with varying degrees of maintenance. So one goal of our project was simply to have an option for Python users. But more broadly, we wanted to bring the common EI methods together with functionality for reporting and visualizing results, quantifying uncertainty, making comparisons, and performing diagnostics in a hopefully efficient and well-tested package that newcomers could get started with. So let me break that set of goals down a little and talk about the Python tools that made them possible. So the top-line results from EI might be single estimates of support within each racial group for each candidate, and PyEI makes it easy to get those point estimates under each of the models implemented. However, as mentioned, a key feature of the kind of Bayesian inference employed in most of these EI approaches is yielding samples from the posterior distribution. So rather than overestimate a single point estimate, like the posterior mean, which would omit a lot of information, we work to give users easy access to information about the whole distribution of posterior samples. So we also made plots like these kernel density estimate plots, KDEs, very usable, user accessible in order to keep the uncertainty associated with the estimates sort of top of mind, hopefully. So for example, our most basic ei.plot generates a plot like this on the left. And similarly, if we look at the estimated differences in votes for a candidate between two groups, we might like to see that as a whole distribution with some uncertainty, with the uncertainty that entails. So leveraging fast gradient-based MCMC sampling, looking under the hood to what enabled these posterior samples that give us a picture of the distributions. For most of our implemented models, we relied crucially on the library PyMC. PyMC allowed us to bring to bear state-of-the-art Markov Chain Monte Carlo sampling methods like the no-U-turn sampler. So PyMC makes efficient MCMC sampling like kind of wonderfully accessible to use. So the syntax here for setting up a PyMC model for the model we saw before is like pretty much exactly what I wrote down on the earlier slide to explain it to you all. So that's really nice. When we started, we were using PyMC3, but we later moved to a sampling method from PyMC version 4 that relied on JAX, just a numerical library that supports auto differentiation, and that gave us significant speedups, which were important for us. So as a unified library for all the models that are in common use, PyEl allows us to make more parallel comparisons between models, where we know that steps like the aggregation of precinct level estimates into polity-wide estimates have been done in the same way across approaches. Moreover, we used other tools from the Python community to ensure that our samples are high quality. So with enough draws, MCMC samples should converge to the true posterior distribution under these models, but in practice, a chain might be too short to have converged, or the geometry of the underlying sampling space might have caused computational difficulties. PyEl uses ArviZ, a Python package for exploratory analysis of Bayesian models, to give convergence diagnostics like R-hat, which compares within chain versus between chain variation and effective sample size. Using PyMC and ArviZ let us have a library that fails loudly when diagnostic values point to the presence of sampling difficulties. So in such cases, we could respond with steps like increasing the number of tuning steps, drawing more samples, reparameterizing, that is moving to a model that's equivalent but where we sample quantities that are transformations of the original parameters, chosen to yield hopefully a less difficult geometry. So in all these cases, right, we can take action because we know there's a problem rather than unknowingly accepting unreliable results. We worked to set up a library with appropriate tests and continuous integration, as the outputs of these models were going to inform real redistricting processes and litigation. We needed a high degree of confidence in our code's reliability. And lastly, we work to provide the kind of documentation and examples that would hopefully make PyEl easy to use, as Chanel will explain in more detail.
So as Karin mentioned before, we definitely knew we'd have a range of audience members for this library. On the one hand, we expected data science practitioners to want to play with some of the statistics and programming behind PyEl, but we also know that a lot of political scientists would want to and have been using this tool. And so we needed to make the barrier to entry pretty low for using PyEl. To that end, there's a set of really useful tutorial, example notebooks that come with the repository, as well as a sample data set that helps to mitigate some of the pre-processing and lets users know exactly what information they need to have to be able to run EI. The tutorial notebooks allow users from start to finish to see what is involved in an EI run, so you fit a model to your data, you can parse the summary, and then figure out how to plot it. The example notebooks actually allow users to compare some of the different statistical methods that make up the EI family and gain a little more intuition into sort of the statistical underlyings of ecological inference. And the reason I think this is so great is that we actually do get feedback from political practitioners who have been able to use PyEl with almost no technical background, and these notebooks provide almost a template for being able to set up full EI runs. So we even had one professor tell us that he was able to do his full run in Google Colab, which I thought was really neat. And now I just want to step back a bit and mention some of the ways that we use PyEl within our lab. As I mentioned before, our collaborators and Professor Knudson may be asked to be expert witnesses on these redistricting litigation cases. Since the start of the 2020 redistricting cycle, PyEl has supported EI in North Carolina, Texas, Wisconsin, Massachusetts, and Maryland. And being in Texas, I do want to talk about it a little. We just did a very involved project here, looking at a number of different things. Professor Duchin was asked to be the Gingles 1, 2, and 3 expert for Texas, which can be a little bit uncommon. And Texas is the second most populous state in the nation. Paired with the fact that we had 39 elections to look at dating back to 2012, we were just dealing with a really huge data set here. One of the main questions we were exploring in Texas was whether Black, Latino, and Asian voters voted cohesively, and whether a coalition claim could be brought in front of the court to say that other voters were voting against this coalition. And we did find some level of evidence of that. I won't go too much into detail. This case is still underway, but one of the big things about Texas was just the size of the data set being so large. We brushed up against some limitations of the high-performance computing cluster at Tufts, but as Karin talked about, there was recently a big update to PyEl, and we're able to use these real-time applications to help us update the library a lot. Having our developers and practitioners work so closely together and often be some of the same people, it really helps us to keep refining this very nimble tool, and allows our maybe non-technical practitioners who want to use the tool to make sure that they're always using up-to-date software. Another thing that's really great and that we look for within EI are regionalized results. So, of course, doing these runs at the precinct level does get different results for each precinct, as opposed to the ecological regression model that Karin mentioned as an example. This really gives us some pretty good certainty that our runs are working. And so just to give a little context for this map here, we're looking at support for Black voters for Lupe Valdez, who was a 2018 gubernatorial candidate here in Texas. And she had really great support in the Dallas area, where she served as the county sheriff for many years before running. And we can also see that in places outside of Dallas, she had a little bit less support. And so these regionalized differences do allow us to create larger stories when we go into court with these cases and say, hey, maybe these people should be grouped together. They might have some of the same ideologies and preferences when you're drawing districts. On a much smaller geographic scale, we've been able to support research in other areas. One I want to talk about is looking at the Chicago City Council districts. At the time of this research, the Chicago Mayoral 2019 election had just happened, where Lori Lightfoot, who is a Black woman, was elected to be the mayor of Chicago. Chicago is sort of an interesting city that, despite the large number of people, white voters were still sort of unwilling to give support to candidates of color. And it was sort of unclear whether the city council districts were gerrymandered or if they were just reflecting the voting patterns happening there. But what we can see here is that white voters in this election actually gave a lot of support to Lori Lightfoot. And so the districts were not actually reflective of the voting preferences of people, and it helped to solidify the case that the districts needed to be redrawn. And so ultimately, while we do use EI a lot in litigation, we can use it in smaller contexts and support a lot of local governments as well. So to wrap up a bit, PyEl is a package that incorporates multiple methods of EI. It's been well tested and developed to be a reliable library for doing EI runs, and it makes critical use of some existing Python libraries. This library constitutes data infrastructure for civil rights, which is something that is growing, but we still don't see enough of, in my opinion. But this package was built from the ground up with clear and focused goals in mind, and moreover, throughout the process, we were attentive to how the software should report and visualize results with clear attention to communicating some of the uncertainty that comes from the EI runs. We worked to provide a lot of practically relevant documentation to support a broad base of users, and it's a very modular library. So if new EI methods are added over time, it'll be really easy to compare them to the methods that are already incorporated into the library now. If anyone is interested in learning more about this and seeing the repository for themselves, we've linked it here. You can feel free to reach out to us with any questions. We have some open issues, and we're always looking for contributors to this repository. Finally, we just want to thank some of the many other researchers that helped to make this happen. And thank you all for listening. Thank you to the PyEI conference for having us. Hope you all enjoyed. Also realizing I said PyEI conference, this is a SciPy conference. I didn't. Slip of the tongue.
A friendly takeover.
Yeah.
It's okay. This room is a PyEI conference, just for now. And we do want to see more social science geared talks, and so it's really exciting to have you all here. We do have several questions in the Slack channel. So from James Lamb, how do you account for the fact that you observe the census data and voting data at different periodicities? The census data once every 10 years and voting data every 2.
There's a couple of ways that we deal with this. One way is just to use the decennial census, but there's another survey, the American Community Survey, that does come out a little more frequently, that tabulates over a 5-year period. And this actually aggregates more voting that's more aligned with, or data that's more aligned with voting, in that it gives citizen voting age population, whereas the census goes as far to voting age population. And so we've used that and been able to directly line up the tabulation years to election years.
The next question from Gwen. How is the accessibility to voter data assured nationwide being an important factor in legislation and visibility of racially polarized voting? Is this included in the Voting Rights Act itself or elsewhere?
I think it's not included in any act that I know of, but I don't know that it's included in the Voting Rights Act. Every state is required to actually put out their election information. The way they do this can vary from state to state. We've worked in some states where they have a very clear website, you can download the files. So I think the accessibility language is there, and then sort of getting into this is exactly what you need to have is not there. Yeah, I don't recall if there was more to the question, so I'm sorry, but
okay.
Yeah.
The next question is, given the large size of your data sets, where did you find the bottlenecks in your analysis? And are there any parallelizable tasks that could benefit from, for example, GPU processing?
Yeah, so I would say there was some parallelization that could happen on the precinct by precinct level, and also as Chanel mentioned, we sort of recently moved to rely on for our PyMC dependent methods. We moved to the newer version of PyMC with a JAX implementation of some of the gradient-based sampling methods, and those, I believe, can make use of GPUs, although we have not yet tried that. So I would be excited to see whether that would give us more speedups.
The next question is from Jonathan March. Thank you, fascinating and crucial. Can you talk a little more about how this impacts detection of gerrymandering or perhaps proving it?
I would say that it lets us look at proposed districts that come out of states and see how many districts are electing the minority candidate of choice. And then it also is mostly used to inform the drawing of new maps. It's sort of a complicated process to get into, but there are many ways of sort of generating scores to say this is how fair or unfair a district is to minority voters based on EI results. And so I think it really helps detect, it helps detect just how representative a map is. But there are many other aspects of identifying gerrymandering as well.
And then, are you able to use kind of external pieces of information, to see if your EI work makes sense, for instance, against exit polls?
We don't really have, full ground truth data. Exit polls may not be reflective of, and typically aren't reflective of the entire turnout. So it's really hard to track down other than asking turnout experts and experts in other aspects of election science if the results make sense. I don't know that we have quite quantified how true to election patterns or voting patterns this is.
Yeah, and I would say there's some work about integrating exit polls in the broader EI space. It's not something that PyEl is like really well equipped to support right now. I mean, so our simplest testing with like ground truth would be simulated data, but there, obviously there's some problems with that because you have to make your assumptions about the simulated data. Yeah, so it'd be great to do more in that direction.
Awesome. I guess, and then probably one last question is, what, if you could ask the SciPy community here for like advancements in tech or something, like what would be the most kind of impactful to this work?
Our lab is hiring, so I think we're hiring for a web development position to really redesign that districtor, which is pretty exciting. But that's a little outside of the specific work. So I don't know, Chanel, if you had a good answer on that.
Yeah, I think there's so many open problems. I know that one of my colleagues has been banging his head like on computational geometry stuff related to redistricting. And so I think it's hard to say that there's one best thing. I think it's more just, if you have an interest, you'd kind of be surprised, or at least I was surprised, the number of different fields that are kind of like overlapping with redistricting in many ways. And I think if anyone has the inclination to do work that would support this, just look up your interests and see, maybe like look up your interest plus redistricting and see if there's any immediate overlap.
Awesome. Thank you so much for such an interesting talk. There's some more questions in the Slack channel, but also some conversation too. I think everybody's been very inspired. This is the last talk of the day. We have a bit of a break and then we'll reconvene for lightning talks in Zlotnick. Thanks.